Right, today we will discuss about robot locomotion. So the type of robot here that will be a mobile robot. Okay, till now we have discussed only about stationary robots, and in the stationary robots, one of the end that is fixed to the base. Okay, here in the case of mobile robot, none of the end is fixed. Okay, so the different type of locomotive systems, okay, which enable a robot to move from one place to another. That is what we are going to mainly discuss here. So mobile robot needs locomotion mechanisms that enable it to move unbounded throughout its environment. But there are a large variety of possible ways to move, and so the selection of robots' approach to locomotion is an important aspect of mobile robot design. So the type of movement that could be walking, jump, run, slide, skate, swim, fly, and roll. So most of these locomotion mechanisms have been inspired by biological counterparts. So here in the next slide, I will show you that how they are related to the biological counterparts. So biological systems succeed in moving through a wide variety of harsh environments. So it is desirable to copy their selection of locomotion mechanisms. So like here in this diagram, we can say. So the first one, the flow in a channel. So there is resistance to that motion, that is hydrodynamic forces, and basic kinematics of motion, that is eddies. Similarly, crawling is there, then sliding in the case of a snake, then running, then jumping. Running, that is commonly here it is shown like a dog or a horse, this type of locomotion. Then jumping, example of a kangaroo. Walking, human being. Because so these type of locomotive systems are also present in a robot. So however, replicating nature in this regard is extremely difficult, because some of the reasons like the mechanical complexity is easily achieved in biological systems through structural replication. So cell division in combination with specialization can readily produce a millipede with several hundred legs and several tens of thousands of individually sensed cilia. So in man-made structure, now coming here, each part must be fabricated individually, and so no such economies of scale exist. So additionally, the cell is a microscopic building block that enables extreme miniaturization. So with very small size and weight, insects achieve a level of robustness that we have not been able to match with human fabrication techniques. Then finally, the biological energy storage system and the muscular and hydraulic activation systems are used in animals and insects. So they achieve torque, response time, and conversion efficiencies that far exceed similarly scaled man-made systems. This stage is currently in developing mode, and further a lot of advancement that is also to be achieved. Okay, due to these limitations, mobile robots generally locomote either using wheeled mechanisms. Okay, so that is a well-known human technology for vehicles, or using a small number of articulated legs. The simplest example of the biological approaches to locomotion. Yeah, so leg type of locomotion and wheeled locomotion. So here the barking. So wheels are human invention and a very popular locomotion concept in man-made vehicles. On the first view, there is no inspiration in the nature for a wheel, but the human bipedal walking, okay, can be approximated as rolling polygon with slides equal in length d to the span of the step. Okay, d, that is the distance which is being covered in one step. Now that is shown here in the figure. So decreasing the step size means that the polygon approaches a wheel. Of course, there is no actively powered wheel which is needed for wheel locomotion in the nature. So nature, we are not having this type of locomotion. So in general, leg locomotion require high degree of freedom and therefore greater mechanical complexity than wheeled locomotion. So here we can compare the wheel locomotion, that is more simple as compared with leg locomotion. So wheels, in addition to being simple, are extremely well suited to flat ground. In fact, the efficiency of wheel locomotion depends greatly on environmental qualities, particularly the flatness and hardness of the ground. Means everywhere that wheel type of locomotion that is not much successful. Surface hardness, flatness that determines. While the efficiency of leg locomotion depends on the leg mass and body mass, both of which the robot must support at various points in a legged gait. So it is understandable, therefore, that nature favors leg locomotion since locomotion systems in nature must operate on rough and unstructured terrain. So the example in case of insects in a forest, the vertical variation in ground height is often an order of magnitude greater than the total height of the insect. So by the same token, the human environment frequently consists of engineered smooth surface, both indoors and outdoors. So therefore, it is also understandable that virtually all industrial application of mobile robots utilize some form of wheeled locomotion. Here in the diagram, we can see some type of this locomotion. So recently, for more natural outdoor environments, there has been some progress towards hybrid and legged industrial robots. Okay, in case of the surface that is not smooth, not flat. In that case, wheel locomotion system that is not much successful. So here, so a hybrid type of both of the system that is suitable for very uneven type of surfaces. The issues in locomotion. The locomotion is the complement of manipulation. In manipulation, the robot arm is fixed but move objects in the workspace by imparting force to them. In locomotion, the environment is fixed and the robot moves by imparting force to the environment. In both the cases, the scientific basis is the study of actuators that generate interaction forces and mechanisms that implement desired kinematic and dynamic properties. So locomotion and manipulation thus share the same core issues of stability, contact characteristics, and type of environment. Under the stability, so number and geometry of contact points. Then center of gravity that has to be maintained. Otherwise, stability, the mobile that will not be stable. Higher the point of contact, so higher stability. So static and dynamic stability, inclination of terrain. Then characteristics of contact. So that could be a contact point or path size and shape, angle of contact and friction. Type of environment, that is the structure or the medium. Either it is on water, air, it is soft or hard,